And especially, so we're going to back up and do this one here first. I don't think we have questions on the homework. Because even though we didn't have homework last night, we still had 1, 1, 1, 2, 1, 3. So I still don't mind going over homework questions that aren't from the immediate last assignment. And I don't mind going back here. Like if, and I was going to say, if it's on like a weekend or something and you see a problem, like we skipped this one, one thing I will say is on the YouTube channel, there's a good chance either 4th hour, 7th hour, or 8th hour covered it. So that's one place to check. But if you forget about that, again, I don't mind backing up. So here, we want to write a function, we'll call it g of x, whose graph is a reflection in the x-axis of the function f of x. So a reflection across the x-axis is going to be negative f of x. So our negative f of x. Now we still just have f of x, we've just thrown a negative in front. So we would replace f of x with its function, and then we would distribute that negative through. Now with the absolute value, the negative times a negative is going to make a positive. So we would just have the absolute value of x plus 2. Our negative times negative 1 is going to be plus 1. And that's it. Questions on this here? We ready to look at horizontal stretch and shrink and vertical stretch and shrink. Vertical stretch and shrink, we'll talk about it first. The general form for vertical stretch and shrink is a times f of x, where a is the amount that the function is being stretched or shrunken vertically. Doesn't matter if it's a stretch or shrink, it's a times f of x, where a is the amount that we're stretching or shrinking. So it says it's a vertical stretch of 2, we put 2 in for a. They say it's a vertical stretch of, or vertical shrink of 1/9, we plug in 1/9 for a. Whatever the stretch or shrink is, it goes in place of a, and we do what we've been doing from there. I do not like how this is phrased for horizontal stretch and shrink, and I'll point it out here. So the graph of y equals f of ax is a horizontal stretch or shrink by a factor of 1 over a of the graph of y equals f of x, where a is greater than 0 and different than 1. I don't like it because they use a in 2 different places. Does that make sense? If it was me, if we're going to say a of x, I want to denote this in some other way than using the same letter twice. I don't know how they would do it. It'd be b of x, where is the graph is y equals f of bx, is a horizontal stretch or shrink by a factor of b equals 1 over a, where a is the given amount in the problem. All that's saying is when we talk about the stretch or shrink, we're going to take whatever that value is and put it as 1 over whatever that number is, whatever that value is. If it tells us it's a vertical shrink of 2, we're going to plug it in as 1 over 2. If they tell it's a vertical stretch of 2/5, I have to flip it, it goes in as 5/2. Does that make sense? Because it's 1 over whatever the amount they tell us. Because 1 over 5/2, 1 over 5/2, well, it would be two, this would be a shrink, is 2/5. So if they tell us the amount that it's stretching or shrinking by is 5/2, we plug in to the function as 2/5. We have to flip it. Now this is the only one where we're actually having to do something to the amount that we're putting in. Okay? Now the first thought is, well, horizontal translation, we did stuff to it. Horizontal translation, if it was left 2, h is -2, we plugged it in as -2. The negative simplified. We didn't actually do anything to it, where here, oh, it's stretching, horizontally stretched or shrunk by 5/2. Okay, I've got to take it, put it as 1 over, flip it. Now we can plug it in. Left, right, it's negative was left, right was our positive value of h. We're not actually having to manipulate it. We're just, this is what it is. Does that make sense? I mean, we're doing stuff, but this, I really feel like we're changing the amount. We have to actually manipulate it. So let's look at vertical stretch first. So we want to write a function h of x, whose graph is a vertical stretch of the graph of f by a factor of 2. Vertical stretch or shrink is a times f of x. That's the general form. A times f of x. How much are we stretching, or well, stretching it by? Factor of what? 2. So the value of a is 2. So what we're saying is we have 2 times f of x. Questions on this here before we move on? Well, what is f of x? Exactly, the absolute value of x minus 3 minus 5. Since we still just have f of x, we replace it. And then last but not least, we've got to multiply through. So we're going to have 2 times the absolute value of x minus 3. We're not going to multiply the 2 through. It's just going to go up front. 2 times negative 5. Negative. That's it. Questions on this here? We're ready for the next one. Let f of x equal the absolute value of x minus 3 minus 5, where is our function, right? A function g, so g of x, whose graph is a horizontal shrink, f of a times x, of the graph of f by a factor of 1/3. Now the value we're plugging in is not going to be 1/3. We're not going to stick 1/3 into that a spot, because it's actually 1 over 1/3. One over 1/3 is 3. What did we really do? We took 1/3 and flipped it. So the actual number we're going to plug in for a is 3. Only horizontal stretch and shrink. Horizontal stretch and shrink is the only one we have to do this with. And it's just part of the horizontal stretch and shrink is just funky that way, because it's similar to, it's not the exact, because horizontal stretch and shrink, we're saying it's increasing faster along the x-axis horizontally, which means it's opening wider. Correspondingly, it's not the same, but vertical shrink did the same type thing. They're not the same, they don't work the same, but it's kind of the same picture. You can see that. There is differences in vertical or horizontal stretch and shrink, but that's about what it's doing. When we stretch it, it's going to open wider. When we shrink it, it's going to open narrower. Does that make sense? So there's it's a little tricky that way. Questions on how we got to here? We don't have f of x anymore. We have f of 3x, which means every x in the function has to be replaced with 3x. Well, we wouldn't leave it like that. We need to get rid of the parentheses around the 3x because we don't need them. There's nothing being applied to it. It's just absolute value of 3x minus 3 minus 5. That's it. Questions on this here? Questions on anything we've done so far? What do we think about horizontal stretch and shrink? Here or there. Because the real trick is just finding that value that we plug in. Once we find that, it's no different than what we've been doing. And again, that's why I like these general forms, because once we figure out which one it connects to, and for vertical stretch and shrink, horizontal stretch and shrink, we figure out the number to plug in. And our translations up, down, left, right, we find the value of h or k, we plug it in, simplify. So here, again, we have another horizontal. Now they tell us the amount that we're stretching or shrinking it by is 5. So it's a vertical stretch, horizontal stretch of 5, yes? So the value we plug in is not 5, it would be what? 1 over 5, 1/5. Because we got to flip 5 to 1/5. So that's the value we would plug in. So we're saying now that we have f of 1 over 5x. Questions on this here? Able to get all that down? Questions on vertical stretch or shrink? You all feel good? Need to see one more? Okay. Yeah, because we've done 2 horizontal, 1 vertical. Write a function h whose graph is a vertical shrink of the graph of f by a factor of 0.25. So h of x is equal to a times f of x. What's the value of a? 0.25. Do I need to do anything to it? We can turn it into a fraction, but besides that, it's vertical, yes? I don't have to flip it. We only flip it or mess with it if it's horizontal. So we can do it as 1/4 or 0.25. 0.25. Now, up to this point, we've been writing f of x, yes? Is there anything that says that I can't just put the 0.25 and the function in at the same time? We've been doing it this way so that we can keep straight step by step. But if you are feeling comfortable with this here, we can put both of those in at the same time. There's nothing that says we can't, but if it helps you to put them in one at a time, we put the 2 in, 2 times 0.25 times f of x. Then write it as 0.25 times, parentheses, our absolute value plus 2. Do that. Because then we'll do the same thing. We're going to multiply by 0.25. 0.25 times the absolute value of x minus 1 plus 0.5. Question for you. Because I know it's a U.S. thing to put the dots. Back home, you normally put a comma for the decimal. Kind of like this here or something like it. If you do that, I'm going to know what you're doing. I'm not going to count off on that because, again, that's just a cultural way of writing things. I have enough wherewithal to realize that you're meaning a decimal point, not a comma. Because even looking at it logically, comma 0.25, we're not trying to signify placeholders. It's going to be a decimal. If I do have a question, I will ask. I'm not just going to immediately nix it. If for some reason I do, ask. Just, hey, this is what it is. And if that makes it essentially would make it right, I'll give you points back. I'm not going to deduct it because I read it wrong. Cancel that. I think we feel good with this now, yes? You ready for the last piece? Combining transformations, let the graph of G be a vertical shrink by a factor of 0.25, followed by a translation 3 units up of the graph f of x equals x. This one here, they stuck the function at the end of the sentence, not at the beginning. The way I want you to treat these, one step at a time. Do the transformations in the order that they are listed. Because changing the order can change how the entire problem looks, and we'll give you an entirely different equation. I don't know if they've showed you that or how that changes it. Not really. They just said we're doing it this way and then called it good. I'll show you. Because this one here, it does. So we're going to start off by vertical shrink by a factor of 0.25. Now, what we name it, I don't care. Because even if we name the first step g of x and then we name the second step h of x, cool, doesn't matter. Because again, g of x, h of x, z of x, m of x, q of x is just a way to name the function. So we can say h of x. Vertical shrink. Our general form is our a times f of x. And our value of a for this is what? 0.25. So we'll fill it in. And I think we all feel comfortable also plugging in f of x. We're going to go put both in, yes? Can we simplify that? Well, yeah, because we have what? 0.25 times x, which is 0.25x. Did we apply our vertical shrink? Yes. Okay. What's our next transformation? 3 units up, yes? We'll call this one g of x. Now, the general form of this, before you write what I'm about to write, we would say that it's f of x plus k, yes? Are we applying this vertical translation to f of x? No, we're applying it to what? H of x. Again, I said f of x is just a way for us to name the function, tell us which one we're applying it to. So here we're not applying it to f of x, we're applying it to h of x because we're wanting to transform this function up 3. So we get that? So in the general forms, we used f as just a general form because that's just standard form. We use f each time. No, what is the function we're applying it to? We're applying it to h of x. And since we're moving it up 3, it means we're going to have plus 3. What's h of x? Which tells us g of x is? Is that any different than what we've been doing? No, we're just doing it one step, one transformation at a time. And the way we've been doing this yesterday and for the first part of today, that's the way I would treat it, one transformation at a time. Some books, some will say, well, because of it's these two types, we can do them at the same time. It doesn't matter. And yes, in some cases, yes. We're able to do more than one at the same time. It's not going to cause issues. It's not going to cause problems. I don't like it because there is some interaction where there can be problems. Same thing in most of the natural sciences, not as bad as some others. For chemistry, mixing salt and water isn't going to do anything. You're fine, you don't need protective gear, you're good. But if we mix an alkaline and a base, or an acid and a base, stuff is going to happen. You're going to need some protective gear. It might not cause any damage or cause you to get hurt. Sometimes it will. So instead of, well, in this cases you need a gear, in this cases you don't need gear. In this, I would rather personally want a way that works every time, no matter the setup, no matter what we have or what transformations. Would we agree there? Because I'm against, you can do it this way if this, and this are true. But if not, then we do it this way where, give me one way that works every time. Let's do it that way. And that's what I'm more of a fan of than try to do stipulations everywhere. Now, I'm going to do this one again. I'm going to flip it. For whatever reason, I'm going to do the vertical translation first. Well, we said K was positive 3, yes? F of X is X, yes? So we simplify, we get we still have the plus 3, we're good, yes? Did that. Now we have a vertical shrink by a factor of 0.25. So our G of X is equal to A times H of X. So we have 0.25 or 2.25 times our X plus 3, yes? So we're still good. 0.25 times X gives us 0.25 X. That still matches up with what we did, so why are we looking at this? Because we would also have 0.25 times 3, which will give us 0.75. Are these the same equation? No. This is where order matters. And it's specifically the order matters because we messed with y in two different places for this function. Vertical stretch and shrink is affecting the output values, the y values. Up and down is a vertical translation. It's moving the y values up and down. Those two interact with each other. Can change, and because of that, they change the formula. Change what it looks like. Changes the outputs dramatically. Now, if it was, say, a horizontal stretch or shrink, followed by a vertical translation, they would not interact at all. Horizontal is affecting the X, the input. Vertical is affecting the Y. They don't interact. Horizontal stretch and shrink, horizontal translation will affect each other. Same with reflections. Now, I like using this one here because it is a very simple explanation to show that, yes, order of how these things will change it. And the easiest way to avoid that, as it lists them, do them in that order. Let the graph of G be a translation 6 units down, followed by a reflection in the x-axis. I'm going to say m of x is equal to f of x plus k. So our k value in this case is 6. Positive or negative? Negative because we're going, and f of x we can just say is absolute value of x, yes? Really, we just subtracted 6. takes care of the first transformation, yes? Second one, reflection in the x-axis. So I'm going to call it n of x. I don't care what it said. Is going to be negative m of x. Because reflection in the x-axis is negative f of x. So in this case, negative m of x. Which for us here would be negative absolute value of x minus 6. And when we distribute the negative through, we would get negative times our absolute value of x plus 6. Since that's the last transformation, we're done. Again, up and down, vertical, affecting the y values. Reflection across the x-axis, affecting the y values. Again, if we did it in the other order, we reflected first, we would have that negative absolute value of x, but then it would be minus 6 instead of plus 6. Questions on this here? You feel good with this here? Okay. That's it. 3 through 6, 11 through 14, 17 through 20, 27, 29.